In this video, I am going to present you some important concepts on statistics for interviews on data science. Now, there is a list of topics I will cover up, but not in a single video. This is a video 1 out of 4 videos, okay? So this is part 1. We start with p-value. What is p-value? P-value is the probability of by chance of getting such data that indicates effect between variables. That means whatever you have got the data, whether you have got it by chance or due to some effect. For example, you see here, this is a time and this side is ticket sales. Now you see that you specify one timestamp t here, and at this moment, entertainment tax was lowered. And you can clearly see that after this time t, there is a rise in ticket sales. Now you have got this data from a sample. Suppose you have taken the sample from one state and there are several states in the country. So from one state you have got this data and it is showing that after t there is a rise in ticket sales. Now the question is whether this data you have got is actually got by chance or it is really due to the effect of the lowering of entertainment tax. So that is the question. So p-value will say whether what is the probability of getting this data which is showing some effect. So what is the probability of getting this data by chance, right? Not probability of getting the data, probability of getting this kind of data by chance. So there is a chance factor, right? So our null hypothesis will be like this: no effect on sales due to the lowering of entertainment tax. Because null hypothesis always deals with neutral, it tries to stay in the neutral position, right? So whatever it matters inside, it always says that, okay, nothing, there is no effect between the variables or like that, right? So our null hypothesis will be no effect. And alternate hypothesis will be just the opposite, that an effect actually exists. Now we assume that the null hypothesis is true. That means there is no effect. Okay. Now based on this assumption, we have to get to know whether we have to reject our assumption or we will not reject the assumption, right? So here is a scale of the p-value because it's a probability value. It starts from 0 and goes up to 1. And this is a probability of by chance, right? So here you go with the threshold of p, that is 5%, that is 0.05. People used to take 0.01 also, and it is up to your choice. So for example, this is the threshold of p is 0.05. Now, if your p-value gets between this range, that means between 0 and 0.05, you say that it is not by chance because p-value measures the by chance of getting the data, right? So it's a very low probability of by chance, okay? So whenever you get a low probability of by chance, you reject the null hypothesis. That means there is an effect going on between the entertainment tax lowered and the ticket sales, right? And on the other side, if your p-value goes a little bit higher, that is more than 0.05 in this range, then you say that the data you have got is by chance. Actually, there is no effect, but this data, this sample is showing something like this, that is having an effect, okay? And this is by chance, right? So in that case, you stay with your null hypothesis and you do not reject the null hypothesis. So this is the role of p-value. Next, we go for linear regression. What it is used to determine the function definition between one or more independent variables, that is predictor variables, and on the other side, you have one dependent or target variable. So it is a function that is mapping on one side with one or more independent variables, and on the other side, you have one dependent or target variable, and you're trying to find out the definition of the function between these two sets. Clear? Now, a function definition is a curve, right? So if the curve is a straight line, then you call that line as line of regression. And that regression is said to be linear regression. For example, you have the screen count on this side and a ticket sale on this side. Now, these are the data points, and based on these data points, we have got this straight line. Now, this straight line is called line of regression. Now, for this line, we have an equation that is y hat equal to h of x. So, h is your function, and it has two terms, w0 x0 and w1 x1. These are added together. And this x0, we call this x0 as bias. So, bias is not an error. Error is something different. Now, this x0 is your bias. Now, this bias is associated with w0. It's a weight. So, the whole term becomes weighted bias. Clear? On the other side, you have this w1 x1. So, x1 is coming from the data set, that is your screen count. And this w1 is also associated with x1. So, this term is also a weighted term, right? Now, you have got w0 and w1. So, these are learning parameters. Clear? Now, you have got x1 from the data set, wherefrom you will get x0. There is no source for x0. So, you set x0 to 1. That is why bias is set to 1. People used to say bias is set to 1. Actually, it is this x0 is set to 1. Now, the point is where from this w0 and w1 will come up. So, these two weights are learned by the algorithm. Okay. So, w0 is learned based on your data, and w1 is also learned based on your data. Clear? Now, how it is learning, that is a different issue. I am not going into details about the linear regression. Actually, it is following one method called gradient descent, and based on that, it is learning this w0 and w1. Now, I will show you just the overview what w0 and w1 is doing here. Now, to find out the best line for best fit so that the error is minimized, you have to rotate the line like this. And for that rotation, w1 is working. So, the weight associated with your data is actually responsible for your rotation or orientation. And on the other side, you will be needing shifting the line up and down. So, for that operation, you need this w0. So, w0 is responsible for shifting up and down, which we call intercept actually. And this w1 is actually meant for rotation, right? So, this is your linear regression. The next topic is Simpson's paradox. A paradox is a confusing situation between the results, right? So, the result obtained before grouping the data and the result obtained after grouping that data, these two results are talking in a different way. It is contradictory to each other, right? And to reveal that reason, there is a third hidden variable which is playing here as a ghost. Now, you go for an example. We take a sample of 1000 viewers and we asked whether they like war movies or not. Now, we found that 820 viewers liked war movies. That means 82% of these 1000 viewers liked war movies. Then you go for another sample with 1000 viewers again, but this sample is not equal to this sample. This is a separate sample. And we get 800 viewers who are liking family movies. So here percentage goes low, 80%, and here 82%. So from this, can we figure out that war movies are more favorable than family movies? Let us go deeper. We've rechecked the data and we found that 800 were men out of these 1000 viewers and 200 were women. And also we found that out of this 820 viewers who liked war movies, 700 of them were men, which is 87.5%, and 120 women out of these 200, right? So that is 60%. So in case of men, it is 87.5% who liked the war movies and 60% of the women who liked war movies. Clear? And this side, we rechecked the data and we found that 600 men were there and 400 women were there. Okay? And out of these 800 viewers, we find that 550 were men, that is 91.67%, and 250 were men out of those 400 women, and that is 62.5%. Now you look at the men's data. The overall data says that 82% is for war movies and 80% for family movies. But here, in case of men only, you see that 87.5% for war, but 91.67% for family. That means in case of men, if you talk to men individually, you will see that these men are liking family movies more than war movies. And in case of women, you say that 60% liked war movies and 62.5% liked family movies. So here also, women percentage for family movies is higher. So when you go for individual analysis between men and women, you find that individually men and women are liking family movies more than war movies. But whenever you go for an overall data analysis, you will see that war movies are more favorable than family movies. So this is a contradiction, right? So this kind of situation is called paradox, and this is known as Simpson's paradox. The hidden variable here is also called a lurking variable. Now, hidden variable here is gender, because gender was not there before. We introduced it, and based on that variable, we find that the result is something different. Now, in this simple example, you have found that, okay, gender, we can use gender, and after that, we can use age also, say above 30 or below 30, like that. You can use for socio-economic status or like that, right? But the point is, in some field, it is very difficult to find out this third and these hidden variables, right? So that is a challenge in those fields. Clear? So before taking decision based on overall data like this, you must introduce these third hidden variables, to find out whether there is a Simpson's paradox existing in the dataset or not. Clear? Next, we go for t-test. Now, t-test is used for hypothesis test for population mean. That is, you have a single population and you want to check whether that mean of the population is equivalent to some specified value or not. And the second one is that hypothesis test for difference of two population means. You want to compare two population means. And the third one is that you want to check whether the population correlation coefficient is a strong correlation or a weak correlation, like that. Okay. So for t-test, you will have no standard deviations available. So this standard deviation sigma will be unknown to you. And when the sample size is small, you can go for t-test. We go for t-test for population mean, right? Now the claim, mean watch time of war movies is 2 hours. So our null hypothesis will be mu equal to 2, and alternate hypothesis mu is not equal to 2. So this is a two-tailed test, because you see that mu not equal to 2, that means mu may be less than 2 or mu may be greater than 2. So on both sides, the mu may be existing. For that reason, it is a two-tailed test. Now we take a sample of 20 viewers on war movies, and it is denoted by n. The sample mean x bar is 2.25 hours. Standard deviation s we calculated as 0.3 hours. It is a sample standard deviation, not the population standard deviation. It is unknown to us. And we set the significance level as 5%. That means a threshold. Okay. So that is 0.005. Clear? We go for the t-score, and this is the formula. Sample mean minus population mean by the standard error, and you will get 3.73. Say we have got 3.73 as our t-score. Now you go for the t-table. We look at the t-table and find out that the t-critical at alpha 0.025. Why 0.025? Because 0.05 is our set significance level. But since it is a two-tail test, so this is distributed between the two tail on the left tail as well as on the right tail. So you divide by 2 and you get this 0.025. So 0.025 on the left tail for the left tail and another 0.025 for the right tail. So we find out the critical value at alpha equal to 0.025, not 0.05. And with the degree of freedom as 19, because we have 20 here as a sample size, so it is -1, n minus 1, so it is 19. And the table says that the range is plus minus 2.093. Now this is our scale. So this side is minus 2.093, this side is plus 2.093, and we get a t-score at 3.73. Now, you do not reject the null hypothesis if your t-score is within this range. But what we see here is that t-score is beyond this range, right? For that reason, we reject the null hypothesis. Clear? Next, we go for t-test to go for testing the hypothesis for difference of two population means. Now, the claim. Mean watch time of war and sci-fi movies is equal. So this is our null hypothesis, that mu1 is equal to mu2, and the alternate hypothesis will be mu1 is not equal to mu2. So this is also a two-tail test. And we take a sample for war movies, that is N1, and that is 20 viewers, with a sample mean x1 bar as 2.25 hours. We go for another sample on sci-fi movies, and that sample N2 is also 20 viewers, and the sample mean x2 bar is 2.10 hours. We set the significance level at 5%, that is 0.05, and we take the pooled standard deviation S as 0.3 hours. The pooled standard deviation actually is a clubbing of two standard deviations for this sample as well as this sample. So standard deviation S1 and this standard deviation S2. So S1 and S2 is clubbed together by a very simple formula. You can go for the text as well as from other resources, and you will find that how to calculate the pooled standard deviation. That means this S1 and S2 is clubbed together to form this pooled standard deviation, and that we found as 0.3 hours. Now this is our test score and a t-score, and this is x1 bar minus x2 bar by this, and we find that 1.58 is our t-score for these two samples. We go for the t-table, and here also alpha is 0.025 because it is two-tailed, and degree of freedom is 38 because for this first sample 20 viewers, n minus 1, that is 19, and here n minus 1, that is 19. So 19 plus 19 gives you 38. So based on this data, the table shows that the range is plus minus 2.024. Now our t-score is somewhere here at 1.58, and it is within this range, right? So we do not reject the null hypothesis. Clear? Next, we go for overfitting. ML model has learned too much details well. That means it has learned so many things and it has gone so deep that it becomes less flexible. That means your model has learned too deeply and too specifically that it has become rigid. Okay? That means less flexible. Right? For example, see, the training is going on and you say that this is a man. This is a supervised learning and you say that this is a man. Okay? The learner knows that this is a man. You add the hairstyle like this here, okay? And say that this is a man and keep on giving examples, lots and lots of examples with the same style of hair, okay? Same style. You keep on giving the data, okay? So the machine knows that, the learner knows that, okay, the hairstyle should be like this, okay? Next, you add a mustache and keep on giving the examples, the same kind of mustache through all the examples, okay? Then you add the jacket as well as the stethoscope, and in most of the examples you have this kind of jacket as well as stethoscope. Now you stop the training and the learner knows that, or your model knows that this is the definition of a man. Okay? Now this is a new data and you ask the model whether this figure is a man or not. Your model says no. Why? Because you see the hairstyle. Your model knows that the hairstyle should be looking like this, but the hairstyle has changed, right? See the mustache. Mustache must be like this, but you have changed the mustache. Here, stethoscope is missing. The jacket is missing. So this is not a man. This is something else. So your model has become too much rigid and less flexible, that if you want to get a result as a man from your model, you have to provide a very near figure like this. A variation in the figure will enable the model to say that this is not a man. Clear? Next we go for underfitting. A machine learning model has learned too less details. This time it is too flexible. Too much flexible, right? For example, keep on training like this. This is a man. Okay? And do not provide too much details so many times. For a little bit time, you just change the data over here and say that this is a man. Okay? So this is a man. And you have a large variation in the figure and you say that this is a man, right? And you stop your training, right? Now you add this hair. The whole figure is the same, but you add the hairstyle like this. And you ask your learner whether this is a man. Your learner says that yes, because it is too flexible. It is a lady, we can see that. But the thing is that your learner is so much flexible that the hairstyle goes like a lady. It says that, okay, well, the hairstyle may be like this, but this is a man. So this is underfitting. So you have to balance somewhere so that you can avoid overfitting and underfitting like this. So see this figure. This is a report from a decision tree model. And this side, you see that the node count is going on. So you increase the node count on this side. And this side is the error. Okay, this side is the error. Now you see that as long as you increase the node count, the error is going down. See the green line, it is a line of the training set. So that as long as the node count is increasing, you keep on increasing the node count, the error is going down. Okay, but the thing is that whenever you consult the test set, the yellow line, you see that initially the error was going down when you were increasing the node count. But after this moment, there is a blue line, this point. After this point, you increase the node count on this side, but the test set is showing the error is increasing. So this blue point, or the blue line, this point is actually the optimized area, the optimized point, right? So this is a good fit. That means you stop increasing the node count if you want to have an optimized model. Okay, so this is this is a rigid, that whenever you are asking for the test set, it is giving you a large error. So this area is the overfitting area, and this area is the underfitting, because if you give too much less node count, then you can go for underfitting, what you have seen before in case of that lady's figure, right? So the most optimized location is this. Now, how will you come to know about this optimized location? You see this, you notice this point. At this point, both the lines, the test set and the training set lines were going down, almost parallel. Not exactly parallel, but almost parallel. It was going down, both of them. But after this point, there is a bifurcation. Test set goes this side and your training set goes this side. So this bifurcation point here is the critical area. So this is the good fit. Okay. So you find out the bifurcation area in your report and you can get an optimized model, right? Next, we go for Bernoulli distribution. In an experiment where there is a success or not success, the outcome is only success or not success. People used to say this not success as failure. So we go for Bernoulli distribution. For example, tossing a coin. Now, tossing a coin means tossing the coin only once gives two possible outcomes only, right? Either it's a head or it's a tail. Now, the trial count is strictly 1. That means you toss the coin only once, okay? So, when you toss the coin once, either you get a head or you get a tail. Now, success is defined as head. You have to define your success. In this example, we are considering head as our success. In your example, you may have tail as your success according to your requirement, right? Now, for head, we will say that the success count is 1. That means how many successes we will have? We will have 1 success whenever we will have a head, and we will have a success count as 0 whenever we will have not head, okay? So whenever we have head, we have a success count as 1. Whenever we will have not head, that is tail, our success count will be 0. That means total number of successes will be 0. Clear? Now, what is the probability of this success count equal to 1? Success count equal to 1 means head. So what is the probability of head? We denote this probability as small p. Clear? In case of fair coin, this is actually equal to 0.5. So we do not know actually whether the coin is fair or not. So we are not saying that probability of success count equal to 1 is 0.5. Okay. So we tell it small p. Clear? What is the probability of success count equal to 0? That means you have no success. That is 1 minus p. Clear? Now, there are 2 equations. Clear? Now, we have to mix this equation in a single equation. We have to club these equations together in a single equation so that from that single equation, both the p and 1 minus p will be the outcomes in specific cases, right? So, how to do that? First, look here. Both the operands must be present in that single equation. And the second thing is that the outcome should be only one of those operands at any moment of time, right? So we go for success count equal to 1. The probability of success count equal to 1 is p. We know that. But there will be 1 minus p also in the equation, in the system. And both the operands will be there like this. And still there will be the output p. So how to do that? You give p raised to 1 because you want a p over here. So definitely p will have a power 1. And now you have to deactivate this 1 minus p section, this term, right? So raise it to 0 so that this whole term becomes 1. And you put a dot operator here so that it becomes p raised to 1 dot 1. So it becomes like this, p raised to 1 dot 1. And this will give you p. Clear? In case of p probability of success count equal to 0, you have P and 1 minus P, both of them. Let me clean this up. And still you want a 1 minus P from this system, right? So what you do, you provide a power 1 to 1 minus P. And if you want to deactivate P now, you provide a 0 over here and you push a dot operator. There is a multiplication operator, right? Now, if you want to have a common equation for these two statements, for these two equations, then what you will have, look over here, you change the 0 to 1 minus 1. And you change this 1 to 1 minus 0. Now, where from this 1, this 0 has come out? See, from this 1, you are getting this 1 as well as this 1. From this 0, you are getting this 0 as well as this 0. And where from this 1 is coming? 1 is coming from here, the trial count. So, if you generalize this equation, then what you get? Probability of success count equal to x. X may be 1 or 0. This may be 1 or 0. And p raised to x, the whatever may be the x, that will be the power of p. We can see here. So, p raised to x. And 1 minus p will be 1 minus that x. So, 1 minus x. So, you can clearly see that these two equations are clubbed together in a generalized form like this. So, this is the equation of Bernoulli distribution. Clear? Now, we go for binomial distribution. What we have seen in the previous slide, when the trial count is 1, probability of success count equal to x will give you p raised to x, 1 minus p raised to 1 minus x. When the trial count is n, and n is greater than equal to 2, there's 2 or more trials now you have, okay? Then what will be the equation? It is ncx and p raised to x 1 minus p raised to n minus x. So you see that this 1, you just follow up that this 1 was coming from the trial count, right? This was coming from trial count. Just you have seen in the Bernoulli's distribution. So now the trial count is n, so it is n minus x. Clear? Now what this ncx is doing here? This is a calculation for the number of ways you can have the success count equal to x. Now, I will give you an example. Now, before that, you just have this in mind that binomial distribution is nothing but Bernoulli distribution for n equal to greater than 2 independent trials. So, binomial distribution is based on 2 or more independent Bernoulli trials. That's all. Okay? Now, for example, in a city, there is a report that 75% of all thefts was due to unemployment. Okay? And 25% of all of those thefts are due to some other reason, right? Now, the question is, out of the next 5 thefts, these thefts have not occurred, okay? So, next 5 thefts, what is the probability of 2 thefts due to unemployment? So, out of those 5 thefts, we want to know the probability of 2 thefts that will be due to unemployment, okay? And 3 thefts will be for some other reason. We don't care about that, okay? So, what is the probability of this? Now, to set up the situation first, you define the success. What is your success? In the previous example, we had the success as head. So, here you have to define what is your success. So, we call that theft due to unemployment is your success, okay? So, you are looking for that, right? Now, the next one, identify existing probability score of success. So, what is the probability of this success, what you have defined? What probability do you have up till now? Okay, so that you find out. That has already been reported. 75%. So P is 0.75. Next, identify the trial count. How many trials do you want to have? In this example, next 5 thefts. That means you are looking for 5 thefts, and out of those 5 thefts, you are looking for 2 thefts probability, right? So those 5 thefts will be your trial. So the trial count N is 5, because this one trial is equal to 1 theft, right? And the last one, identify success count. Okay, so we want 2 thefts as a success count. So expected success count is 2. This expected is not actually your expectation in statistics. Expected means we want to know actually the success count is 2. Okay. So see, 5 thefts. Out of those 5 thefts, we are interested in 2 thefts and probability of those 2 thefts due to unemployment, right? Now the theft can be had in here and here, in these 2 cases, or 1 and 3, or 1 and 4, or 2 and 5, or 3 and 4, like that. So many ways the 2 thefts may be there which are due to unemployment. For that reason, NCX is working here. N choose X. Okay. So P of success count equal to 2 is 5C2, because 5 thefts are there. Out of 5, you have chosen 2. So 5C2, P raised to 2, 1 minus P raised to P N minus X, that is 5 minus 2. And this probability will give you 0.09. So there is a 9% chance that out of the next 5 thefts, 2 thefts will be due to unemployment. Clear? So this is binomial distribution. Next, types of errors. See this table? If the hypothesis is true, this is hypothesis true, this is hypothesis false. So if the hypothesis is true in fact, but you reject the hypothesis by mistake, then that is called type 1 error. And if the hypothesis, the null hypothesis, is false, but by mistake you do not reject the null hypothesis, then it is type 2 error. So accept is actually do not reject. It is better to use like this. You do not accept null hypothesis. You do not reject null hypothesis, because null hypothesis is always assumed to be true. Okay, so if you assume to be true, then what is the use of acceptance, right? So you do not reject the null hypothesis, but in fact, the null hypothesis what's showing is false. So it is a type 2 error. Now for type 1 error, mathematically or statistically you can say probability of rejecting null hypothesis when it is true. It's a measurement, right? So type 1 error is something like this, that null hypothesis is in fact true and you are rejecting it. That is an event, that is a term. But statistically, it's a probability of rejecting null hypothesis when it is true. Clear? Now, for example, we have this null hypothesis. Genre has no effect on scores. Thus, the population mean scores are statistically equal across 2 types of movies. That means you have a comedy movie at one type and sci-fi movie as type 2. The mean score given by the viewers here is mu1, and the mean score given by the viewers here is mu2. So the null hypothesis says that mu1 is equal to mu2, right? Now you go for the same scale as we have done before, that 0 is no chance factor. That means the data we got actually is not by chance. It has some effect. And the other side is extreme chance factor. That means it is 100% by chance we got the data. Actually, it has nothing to do with the population. Okay, so this side is the sample has nothing to do with the population, and here on this side the sample has something to say valid about the population. That means whatever the sample will say to you, that is valid for your population. So these are the 2 extremes we have. And likewise, we have this threshold of P, it is, for example, 0.05. So this is not by chance, we have seen before. So you reject the null hypothesis. And if your P value falls here, that means you have got by chance, actually it has nothing to do with the population, so you do not reject the null hypothesis. Now this is the thing, that there is a 5% chance of making type 1 error. That means when you are going for rejecting, so this portion is rejecting, right? Now when you are rejecting the null hypothesis, you have a chance of 5% error or 5% mistake, right? The thing is that you are dependent upon the sample. You do not have the population. You have the sample. The sample is the representative of the population. Now, based on the sample, you are rejecting the null hypothesis, when in fact the null hypothesis is true. So what is the range of mistake can you have? So that is a 5% chance. Next we go for central limit theorem. Suppose there is a population and the mean is mu and variance sigma square. You have a sample and the sample is mean is x bar and the variance is sigma square by n. Now you see here that as the sample size tends to large, that means n greater than 30, the sampling distribution of the sample mean tends to normal distribution. That means you increase the sample size and the sampling distribution of the sample mean tends to be normal. For example, you see this is already a normal population you have, and this is x and this is f of x. Now when you have n equal to 2, you have a distribution like this. For a normal population, you have a sample distribution like this of your x bar, and you increase the n to 5 and your height goes a little bit higher with a little bit narrower, and here you have n equal to 30 and you have this figure. So it is taking the shape of a purely normal distribution. Clear? Now in case of uniform population means you have the data from here, the range is R1 and R2, and between this R1 and R2 you have a value of y as a fixed point, right? So same y between R1 and R2, right? So this is uniform population. So there is no variation or change in y with respect to x, right? So whenever you have this n equal to 2, you have a figure like this. N equal to 5, the figure goes like this, and n equal to 30, it is like this. For binomial population, remember this binomial population is discrete, so we are dealing with probability because we are dealing with frequency. So this side is x and this side is probability of x, and we have a figure like this, initial figure. Now we go for n equal to 2, the figure goes like this, n equal to 5, this, and n equal to 30, it is like this. And the last one, exponential population, initially it was like this, then n equal to 2, n equal to 5, and n equal to 30. So every time you see that, whenever the sample size goes larger, the sample means distribution tends to be normal distribution. So this is the statement of central limit theorem. This is the last topic in this video, and we have skewness or asymmetry. That means how much the distribution is asymmetric. So that measure is skewness. Clear? See this example, see this figure. This is purely a symmetric distribution. So there is no asymmetricity, right? So if the left tail, that means this tail, and the right tail, that means this tail, are equal, we get a symmetric distribution. We get a symmetric distribution for which mean, median, and mode are same. Here you see that at 40, this yellow one is the mean, this one is mean, this one is median, and this one is mode. So mean, median, and mode, all of them are standing at 40. whenever you have a symmetric distribution. Clear? Now, this is a left skewed distribution or negatively skewed distribution. So, if the left tail is longer, so this tail is longer. You see, this one is longer, this one is shorter. So, whenever you have this left tail is longer, we have negatively skewed distribution for which mean is less than median, less than mode. So, yellow is the mean. So, 47 is the mean, 50 is the median, and 60 is the mode. So, you can see that mean is less than median, less than mode. And this is called rightly skewed or positively skewed distribution if the right tail is longer. And here you see that mean is greater than median and greater than mode. So, mean is here, mean is greater than median and greater than mode. So, in all the three cases you see that median is always standing between these two measurements, right? And in this case, in the negatively skewed distribution, you have mean on the leftmost side and mode on the rightmost side. And here on the positively skewed or rightly skewed distribution, you have mean on the left-hand side, mean on the right-hand side and mode on the left-hand side. That's all in this video for part 1 for these topics. We will continue with more topics in part 2 of this discussion.